Hey guys, tonight we are exploring the standard model of particle physics. But don't worry, you don't need to be a physicist to understand this lecture. Before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And let me know in the comments where you are tuning in from and what time it is for you. It's always fascinating to see who's joining us from around the world. Now, dim the lights. Maybe turn on a fan for that soft background hum. And let's ease into tonight's journey together. Take a breath. Feel that? You just inhaled about 25 billion trillion molecules, each one dancing, vibrating, following rules so precise that we can predict their behavior with mathematical certainty. You're not just lying in your bed. You're immersed in the universe's greatest symphony. And tonight, I'm going to teach you to hear the music. Everything around you, your bed, your pillows, the air, the light in your house, even your own thoughts, follow the same fundamental laws. It's like discovering that every song ever written, from Beethoven to Beyoncé, uses the same 12 musical notes. The standard model of particle physics is our sheet music for reality itself. By the time we're done today, you'll understand how the universe builds everything from just 17 fundamental ingredients. You'll see why a star exploding billions of years ago created the calcium in your bones, and why every chemical reaction is really just particles playing elaborate games of cosmic tag. This isn't just theory. It's the operating system of existence. Imagine walking into the world's most incredible Lego store, but instead of thousands of different pieces, you discover something extraordinary. Every single creation in the entire store, castles, spaceships, cities, works of art, was built using just 17 different types of blocks and 4 ways to connect them. That's our universe. Everything that exists is constructed from 17 fundamental particles held together by 4 fundamental forces. It's the ultimate example of less is more, infinite complexity arising from elegant simplicity. But here's what makes this even more remarkable. We didn't figure this out by carefully taking things apart with tweezers. We discovered it by smashing particles together at incredible speeds and watching what flew out. Like trying to understand how a Swiss watch works by shooting it with a cannon and analyzing the debris. Somehow, this violent approach revealed the most beautiful, delicate structure imaginable. Think of the standard model as nature's recipe book. Just as a master chef knows that every complex dish breaks down into basic ingredients and fundamental cooking techniques, physicists have discovered that reality has its own essential ingredients and basic preparation methods. The particles are our ingredients, the forces are our cooking methods, and the result? Everything you see, touch, taste, or dream about. Let me take you back to the 1950s and 60s. Picture physicists as detectives who've just walked into the world's most confusing crime scene. New particle accelerators were like witnesses who couldn't stop talking, revealing dozens of strange new particles, each existing for barely a trillionth of a second before vanishing or transforming into something else. It was chaos. Scientists were discovering particles with whimsical names like strange, charm, and beauty. Not because physicists were trying to be poetic, but because these particles behaved so oddly that ordinary language broke down. Some seemed to violate conservation laws. Others appeared to exist in families, like having identical twins with slightly different weights. The breakthrough came when brilliant minds like Murray Gell-Mann started looking for patterns. It's like walking into a room full of complex Lego sculptures and suddenly realizing they're all built from the same basic blocks. The apparent chaos was hiding a beautiful order. Gell-Mann proposed something revolutionary. What if protons and neutrons, particles we thought were fundamental, were actually made of smaller pieces? He called these pieces quarks, borrowing from James Joyce. 3 quarks for Muster Mark. This was like discovering that atoms, which literally means indivisible, could themselves be divided. It was layers all the way down, each level revealing deeper simplicity beneath apparent complexity. The pattern emerged, just as chemistry showed us that hundreds of substances were built from about 100 atoms. Particle physics revealed that dozens of particles were made from just a handful of truly fundamental building blocks. By the 1970s, the Standard Model was born, our unified theory of matter and forces. It was humanity's greatest act of reverse engineering, figuring out the universe's blueprint by studying the pieces. Now let me introduce you to the universe's essential players. Think of them as the periodic table of absolutely everything, the basic cast members in reality's ongoing drama. Quarks are the universe's ultimate team players. They come in 6 varieties, 6 flavors, as we call them: up, down, strange, charm, bottom, and top. These names have nothing to do with direction or taste, they're just labels, like calling people by their first names. Here's the beautiful part. Everything solid you've ever touched is built from just 2 quark flavors. Protons are made of 2 up quarks and 1 down quark. Think of it as nature's favorite 3-ingredient recipe. Neutrons flip that, 2 down quarks, 1 up. That's it. Every atom in your body, every element on Earth, every star in the sky, it all comes down to different arrangements of these simple 3-quark combinations. But nature has an iron rule. Quarks can never appear alone. It's like having Lego pieces welded together the moment they touch. Try to isolate a single quark and you won't free it. You'll just create new particles. The universe seems to say, quarks must always have company. This rule, called quark confinement, is one of the deepest mysteries in physics. It's as if nature has a social worker ensuring no quark ever gets lonely. The heavier quarks, strange, charm, bottom, and top, are like the exotic cousins in the quark family. They don't exist in ordinary matter, but we can create them in high-energy collisions. They're unstable, quickly decaying into the familiar up and down quarks, like house guests who can't stay long. While quarks are forced into groups, leptons are the universe's individualists. They can exist perfectly well on their own. The electron is the most famous lepton. The particle that makes chemistry possible, carries the current through your phone charger, and enables you to see by interacting with light. Every chemical bond, every electrical device, every biological process depends on electrons doing their job with incredible precision. But electrons have 2 heavier siblings, the muon and the tau. Think of them as different sizes of the same tool. A muon is about 200 times heavier than an electron, while a tau weighs in at about 3,500 times an electron's mass. They're like having a screwdriver, a wrench, and a sledgehammer. Same basic function, very different scales. Each charged lepton has a ghostly partner called a neutrino. These are the universe's ultimate introverts. Right now, billions of neutrinos from the sun are passing through your body every second. You don't feel them, you don't see them, they don't interact with anything. They're so antisocial that a neutrino could travel through a light year of solid lead and have only a 50-50 chance of hitting anything. Yet, neutrinos carry crucial information about cosmic processes. They're like cosmic messengers that travel straight line from the most violent events in the universe directly to our detectors, carrying news from the hearts of exploding stars and the cores of distant galaxies. If fermions, like quarks and leptons, are the universe's building materials, bosons are the mail service. They carry messages between particles, telling them how to interact. Every force in nature has its own postal system. Photons are pure energy messengers. Every beam of sunlight, every radio wave, every Wi-Fi signal is made of photons racing around at light speed, carrying the electromagnetic force. When you see anything, you're detecting photons that bounced off objects and reached your eyes. When you take a photo, your camera is capturing photons. When you heat food in a microwave, you're bombarding it with photons. Photons are literally how the universe shares information about itself. Here's something mind-bending. A photon doesn't experience time. From its perspective, it's created and absorbed in the same instant, no matter how far it travels. The photon hitting your eye from a distant galaxy doesn't know it traveled billions of years. To the photon, that journey was instantaneous. These particles carry the weak nuclear force, the power behind radioactive decay and the fusion reactions that make stars shine. They're like photons' heavier, shorter-lived cousins. While photons are eternal wanderers that can cross the universe, W and Z bosons exist for only about 10 to the minus 25 seconds. They're like mayflies of the particle world, incredibly brief lives, but absolutely essential for cosmic processes. Without the weak force, the sun would be cold and dark. The fusion reactions that power stars depend on weak interactions to convert protons into neutrons. No weak force means no stellar fusion, no sunshine, no energy to power the chemistry of life. The weak force is also responsible for creating heavy elements in stellar cores. When massive stars explode as supernovae, weak interactions help forge elements like iron, gold, and uranium, the heavy atoms that make planets and life possible. Gluons carry the strong nuclear force, nature's most powerful adhesive at short range. They bind quarks together inside protons and neutrons, creating the atomic nuclei at the heart of every atom. But gluons have a unique property. They're sticky to themselves. It's like having glue that glues to itself, creating an increasingly tangled mess. This self-interaction makes the strong force behave very strangely. Instead of getting weaker as you pull particles apart, it gets stronger, like a cosmic rubber band that stiffens under tension. This is why you can never isolate a single quark. Put enough energy into trying to separate quarks, and you'll create new particles rather than breaking the original bonds. It's nature's way of saying, nice try, but the rules are the rules. The Higgs boson is connected to a field that permeates all of space, the Higgs field. Imagine the entire universe as a cosmic swimming pool filled with invisible, massless honey. As particles move through this Higgs honey, they interact with it differently. Some particles wade through easily, staying light. Others struggle against the field, becoming heavy. Photons glide through without interacting at all, remaining massless and traveling at light speed. The Higgs field is like a cosmic tailor, fitting every particle with exactly the right amount of mass for its role in the universe. Without this field, electrons would race around at light speed, atoms couldn't form, and reality would be nothing but a chaotic sea of massless particles. The Higgs mechanism is so fundamental that finding the Higgs boson required building the most complex machine humanity has ever created, the Large Hadron Collider. When we finally detected it in 2012, it was like finding the universe's mass production factory. Understanding the fundamental forces is like learning the basic grammar of reality. Once you know these rules, you can see how they combine to create all the complexity we observe. Gravity is physics' greatest paradox. It's absurdly weak. The electromagnetic force between two protons is about 1 trillion trillion times stronger. Yet gravity shapes the entire cosmos. Why does this weakling dominate? 2 reasons. Gravity has infinite range, and it only attracts. It's like the most patient person at a party. Not very forceful, but eventually everyone ends up talking to them. When you drop your pen, you're witnessing something profound. Every atom in Earth is pulling on every atom in that pen. The pen must respond. It has no choice. But here's the beautiful reciprocity. The pen also pulls on Earth with exactly equal force. Earth moves toward your pen, just by an unimaginably tiny amount. Gravity is geometry made manifest. According to Einstein, massive objects don't pull on other objects. They curve space-time itself. Imagine rolling a marble on a stretched rubber sheet with bowling balls scattered across it. The marble doesn't know about the bowling balls. It just follows the curved paths they create in the sheet. This is the force that makes your world possible. Every chemical bond, every biological process, every thought firing through your neurons depends on electromagnetic interactions. Right now, electromagnetic forces between electrons in your body and electrons in your chair are preventing you from falling through the floor. When you walk, it's electromagnetic repulsion between atomic electron clouds that gives you something to push against. Electromagnetism is incredibly versatile. It can attract or repel, build complex structures, carry information across vast distances, and power virtually every technology we use. Light is just electromagnetic waves propagating through space, different frequencies giving us radio, microwaves, visible light, X-rays, and gamma rays. It's all the same phenomenon, just vibrating at different rates. Your cell phone works by manipulating electromagnetic fields with extraordinary precision. We've learned to encode information in electromagnetic waves, send it through space at light speed, and decode it with perfect fidelity. The strong force works only at incredibly tiny distances, smaller than an atomic nucleus. But within that range, it's overwhelmingly powerful. It holds protons and neutrons together in atomic nuclei, overcoming the electromagnetic repulsion between positively charged protons. Think of the strong force as nature's ultimate zip tie. Once engaged, it's nearly impossible to break. But it only works when particles are practically touching. This is why atomic nuclei are so incredibly stable, and why nuclear reactions release so much energy. The energy stored in strong force bonds is staggering. A single uranium nucleus contains about 200 million times more energy than a typical chemical bond. That's why nuclear reactions are so much more powerful than chemical reactions. We're tapping into the fundamental binding energy of matter itself. Nuclear power plants work by carefully breaking these incredibly strong bonds. Fusion reactors try to form new ones. In both cases, we're accessing the energy bank account that nature has been saving for billions of years. The weak force is nature's shapeshifter. It can change one type of particle into another. This is the force behind radioactive decay, where unstable nuclei transform into more stable configurations by converting protons into neutrons, or vice versa. This might seem like a minor supporting role, but the weak force is actually crucial for cosmic evolution. It powers the sun by enabling fusion reactions that convert hydrogen into helium. It creates heavy elements in stellar cores. When massive stars explode, weak interactions help distribute these elements throughout space. Without the weak force, the universe would contain only hydrogen and helium. No carbon, no oxygen, no silicon, none of the elements that make planets and life possible. The weak force is nature's cosmic recycling program, transforming simple elements into complex ones. What makes the Standard Model truly extraordinary isn't just that it explains what we observe. It predicts phenomena we haven't discovered yet, with stunning precision. In the 1960s, physicists used the equations of the Standard Model to predict that W and Z bosons must exist. They calculated exact masses, decay patterns, production rates, all based purely on mathematical consistency. It was like using architectural blueprints to predict exactly what kind of foundation stones you'd find if you dug in a specific location, down to their chemical composition and structural properties. When these particles were finally discovered at CERN in 1983, they matched the theoretical predictions almost perfectly. The W boson had exactly the predicted mass. The Z boson decayed exactly as calculated. It was one of the most spectacular confirmations in scientific history. The top quark hunt was even more dramatic. Theory predicted this particle should be incredibly massive, nearly as heavy as an entire gold atom. Creating top quarks required the most powerful particle accelerators on Earth, smashing protons together with tremendous energy. The Standard Model not only predicted the top quark's existence, but calculated its mass to within a few percent. When it was finally discovered in 1995, it was like an architect predicting exactly where to find a specific cornerstone in a building's foundation, and having construction crews find it precisely where the blueprints indicated. The Higgs boson hunt was perhaps the most ambitious scientific project in history. Based on theoretical work from the 1960s, physicists knew they needed to find this particle to complete the Standard Model. The search required building the Large Hadron Collider, a 27-kilometer underground ring where protons race around at 99.99999% the speed of light, before smashing together with energies comparable to cosmic ray collisions. When the Higgs was finally discovered in 2012, after decades of searching, it was like completing a 50,000-piece jigsaw puzzle and finding that the final piece fit perfectly. The particle had exactly the properties theory predicted. Mass, decay patterns, interaction strengths, all matched the mathematical expectations. These weren't lucky guesses. The Standard Model made precise, quantitative predictions that were confirmed by experiment.
Now, here's where our story becomes truly exciting.
Despite its spectacular successes, the Standard Model is like a detailed map of a continent, with several unexplored regions marked, "Here be dragons." When astronomers began observing galaxies, they discovered something shocking. These cosmic pinwheels were spinning too fast, and the visible stars and matter didn't provide enough gravity to hold them together. It's like watching a figure skater spinning faster than should be physically possible. Something invisible must be there, something with mass, that creates gravity but doesn't interact with light. We call it dark matter, and it appears to make up 85% of all matter in the universe. Here's the problem. The Standard Model contains no suitable dark matter candidates. Every particle we know either interacts with light, making it visible, or is too unstable or lightweight to explain what we observe. It's like having a complete recipe for a cake, but being told that 85% of the ingredients aren't listed in your cookbook. Dark matter is nature's ultimate cosmic hide-and-seek champion. It's there, we can see its gravitational effects, but it refuses to reveal itself through any of the forces in our Standard Model, except gravity. Even stranger is dark energy. The universe isn't just expanding, that expansion is accelerating. Galaxies are flying apart faster and faster, as if someone keeps pushing harder on the cosmic gas pedal. Some unknown form of energy is pushing space itself apart. And this mysterious energy makes up about 68% of everything that exists. Picture blowing up a balloon, but instead of your breath running out, the balloon starts inflating faster and faster on its own. The Standard Model has no explanation for dark energy. It's completely outside our current framework of fundamental physics. We're like cartographers who've mapped every stream and hill in our local area, only to discover that most of the world consists of entirely unknown terrain.
Why is gravity so embarrassingly weak compared to other forces?
You can overcome Earth's entire gravitational pull by lifting a paperclip with a small refrigerator magnet. This enormous disparity suggests we're missing something fundamental about the nature of space, time, or forces themselves. In the early universe, equal amounts of matter and antimatter should have been created. When matter meets antimatter, they annihilate completely, producing pure energy. So why didn't everything cancel out moments after the Big Bang? The Standard Model allows for some matter-antimatter imbalance, but nowhere near enough to explain our existence. It's like trying to explain why one team won a championship 1,000-0 when the rules only allow for a 1-point advantage. We now know that neutrinos can change from one type to another as they travel through space, a phenomenon called neutrino oscillation. This requires neutrinos to have mass, but the original Standard Model assumed they were massless. These ghostly particles are telling us that our theory is incomplete. They're like witnesses to cosmic processes we don't fully understand, carrying information about physics beyond our current knowledge. As I look at you, the next generation of thinkers and discoverers, I'm filled with excitement about what you might achieve. The Standard Model is not the end of physics, it's the foundation for everything that comes next. Some of you might become the physicists who finally detect dark matter particles, unlocking 85% of the universe that remains hidden. Others might develop the unified theory that includes gravity, or solve the mystery of why matter exists at all. But even if you never set foot in a laboratory, you can carry forward something precious. The understanding that the universe makes sense. Beneath the apparent chaos of daily life lie elegant, discoverable laws. The same mathematical principles that govern the most distant quasars also determine how atoms dance in your coffee cup. You are made of particles forged in the nuclear furnaces of dying stars, held together by forces that have remained constant for nearly 14 billion years, animated by the same energy that powers galaxies. You're not separate from the cosmos. You are the cosmos, evolved to the point of self-awareness. The Standard Model represents humanity's greatest intellectual achievement, using mathematics to decode the fundamental operating system of reality. Every equation we've discussed, every particle we've named, every force we've described, represents the collaborative work of thousands of brilliant minds across decades of patient investigation. But this story isn't finished. The mysteries that remain aren't obstacles. They're invitations. Nature is saying, "You've done well so far, but there's so much more to discover." Keep asking questions. Keep pushing boundaries. Keep exploring. The universe gave us brains capable of understanding quarks and bosons and quantum fields. It seems almost like the cosmos wanted to understand itself and evolved us to do the job. You're part of that grand project, the universe's ongoing attempt to comprehend its own nature. Every time you ask why, every time you solve a problem, every moment you spend trying to understand how reality works, you're participating in the most important adventure our species has ever undertaken. Welcome to physics. The greatest discoveries lie ahead, and some of them might come from minds sitting in this very room.